Good morning, everybody. Thank you, Corey, Rochelle, Brandon, Del Dodson. Thank you. Thank you. Well, as I, yeah, for the time being, let me change the camera. Well, we are, uh, we are right here at this time. Um, Today's April 4th. But as you see, I am a little bit behind because I spent more time on section 16.4, which is an extremely important section, by the way. And as a result, I'm 1 week behind. Today, I will start 17.1, but there are a lot of material in 17.1. And I don't think that I'm going to follow this uh, spreadsheet anymore because of the significance of the material remaining. Um, so uh, today I will start chapter 17. And chapter 17 is about graphing, right? Is about graphing. Now, when it comes to graphing, let me take you to calculus uh, or even pre-college college algebra, pre-calculus. When you are dealing with a function of one variable in calculus 1, the graph of this function is defined to be the set of all x's, y's, such that y is f of x, all right? So you put all the point x, f of x's together, and so theoretically, this is called the graph. But if you plot these points and join them, you will get a picture of that graph. Here is, for example, y equal x squared. So the way we graph it here, we choose the set of all points, x, the y coordinate is x squared, and join these these points, all right, and we will get this parabola. When we get to calculus 3, if you remember, now the functions, we dealt with functions of two variables. The input is a point, xy, ordered pair, and the output is when it comes to geometric interpretation, the output, we thought about it as the height for that point. So we put them together, you will get the input, comma, the output, all right? This is a point in 3D. So graph of a function of two variables is a 3D object. For example, here is z equals 4 minus x squared minus y squared. So theoretically, the graph is this, the set of all points, the input, but the z value you calculate from here. Then you plot these points in 3D and join them, and you will get this, right? This circular paraboloid, which is a surface. a three-dimensional object. But when it comes to a function of four variables, x, y, z, if we want to follow the same rule, by the same rule, I mean, put the input is x, y, z, the output is calculated by this rule. You will get a point in 4D, four-dimensional point. So, although we can explain it theoretically, saying that, okay, this is the graph, but unfortunately, we do not have, we cannot visualize, we cannot have a geometric shape, we cannot. Okay, so this is a problem, right? This is a problem. So the same thing happens in vector field, of course. We do have the same problem with vector fields. And now, when it comes to complex analysis, the input of the function is x plus iy, that we can interpret this as an ordered pair xy. When you plug it in, you will get a real part plus I imaginary part, another ordered pair, this time UV, right? Now, again, if I want to follow that pattern of calculus 1, we got to say, okay, graph is this. The input, which is x, y, comma, the output. But again, this is a four-dimensional point, right? The input xy, the output uv, it's a four-dimensional. So we cannot follow the same pattern as graphing a function when it comes to complex. What is the solution then? Oh, solution is here. We will have two coordinate axes. One for inputs, the other one for the output, all right? So the coordinate axis, we choose the input from here. And we plot the outputs in the other coordinate axis. So here are the outputs. Or the values of the function. So that is the solution. We are going to have two coordinate axes. And usually the problem that we want to solve in this mapping, let's call it mapping. The question is, they will give you a region of XY plane, for example, a circle. And they will ask you, okay, what is the image of that circle here under this function? So that is the problem that we will be concerned with. And today, I will start with very easy mappings, and we will build on them. Please pay good attention. The easiest one, the very basic one, is rotation. What is rotation? By the way, again, although I said we are going to consider two coordinate axes. Sometimes we put these two coordinate axes on top of each other. For example, here is the point Z. I want to rotate Z 90 degree. And when I say 90 degree, that means in positive direction, and positive direction would be counterclockwise. So if I want to rotate this 90 degree, it becomes right here, right? So if the original argument of Z is theta, I am adding to it another pi over 2. So this point will have the same modulus, but its argument will be theta plus pi over 2. Right? That is called rotation. In general, here is the point Z, r e to the I theta, all right? Here, this is r, the modulus. If I rotate 90 degree, that means actually I am multiplying by e to the pi over 2 I, because r doesn't change, only the theta, the argument, will be changed, and you are adding to it pi over 2. So it is multiplication by e to the pi over 2 I. That is rotation 90 degree. How about if I want to rotate alpha degree? Well, rotation of alpha degree is right here. You simply multiply by e to the I alpha. Okay? So that is one of the very basic motions in geometry, rotation. Okay, next one. Any questions so far? Please interrupt me if you have any question. All right, Hennessy, no question. Here comes another geometric motion, which is called translation. What is translation? Well, here is the point, Z. You take Z to another point. You simply move Z to another point by adding a number a plus bi. So if this is x, you are adding a. If this is y, coordinate of z, you are adding b. So you get to this point, all right? So putting it in two different coordinate axes, z is here, but z plus a plus bi. Just let's call this one b. This is z plus b. All right, this is b. This is called translation. We move a point or a region parallel to x-axis and parallel to y-axis. All right, the motion is always parallel to x-axis, parallel to y-axis. That is called translation. There is another one, which is called expansion or contraction. And that's when you multiply by a constant, right? Here, this is z. I simply multiply that by a number. That A, well, definitely a positive number, all right. So the A is a positive number. Now, if A is bigger than 1, we are not changing. Look, A is a positive real number. We are not changing the uh, theta. It will be on the same ray, okay? Only the modulus, which is R, changes. It will be AR. If A is bigger than 1, it of course goes there, which is called expansion. If here is 2 multiplied by 2. If A is less than 1, then it will shrink, come closer to the origin, and that's called contraction. All right. So 3 motions: rotation, translation, this expansion or contraction. Putting this 3 together, right, here is when A is bigger than 1, it is expansion. When it is less than 1, it is contraction. We put these 3 together, and we will have a linear function. Oh, let's look at this. A linear function. A and B are complex numbers. A being a complex number, we can write it as this. That is when I said A is a positive quantity. So when you multiply Z by A e to the I alpha, you get this. And here is B. Well, look, this is Z multiplied by A. So the first thing we do is expansion or contraction. Right after that is a rotation by alpha. And after rotation, we have translation. So combination of these 3 will give us a linear function. Linear function means it is just a number times Z plus a number. We don't have Z squared. We don't have e to the Z. No, it's just Z. That's called linear. All right, let's have one little example here. Please understand this 3 motions. So whenever you have a linear function or mapping, right now we are dealing with the concept of mapping. Here's when I said A is modulus of A, all right, with previous notations. So when you have AZ plus B, the first thing you do, you multiply by modulus of A. This is magnification or contraction. This is called magnification in general. Then you multiply by e to the, well, I better say alpha to be consistent with previous notations. So you multiply by e to the I alpha. That part is rotation. So magnification, then rotation, and of course, at the end, translation. Okay, good. Here is one example. Usually, they will give you a region. Here is a triangle. And they will ask you, what is the image of this? What happens to this if we apply, for example, a complex function? Here, we want to apply this, 2z plus 1 minus 2i. But there is a fact involved here. Whenever we apply a linear function, whenever we apply a linear function, the lines will be mapped onto lines. So a line cannot be a curve then, it's a line. So in order to find the image of this under this function, we better just find the image of these 3 points and then join them. Okay, join them. So these hugs. So what is image of 0 under this function? If you put 0 here, you get 1 minus 2i. What is image of 5 plus I? Point P. And here's point Q. Oh, you plug in here and find the image here. So 0 will be mapped to this one, P here, Q here. Putting them together in UV plane, this is the image. So after we apply that function, that triangle, that earlier triangle, will become this in UV plane, all right, in UV plane. So here is 11. And here is 1 minus 2i, and here is 9 plus 4i. Okay. Any comment, any question? This is what we are going to do in chapter 17. We will apply different function to different regions, right? In this case, we applied this linear function, and the question was, what will be image of this after we apply this function to it? And here is the image. Using the fact that, of course, when you are dealing with the real function, straight lines will stay straight lines, okay? That was a sort of key and shortcut to our solution. Next, I want to talk about the function z squared, okay? Let's look at the function z squared. Well, there are two ways to write the values of the function. One, by letting Z be in its uh, polar format or exponential format. The other one is letting Z be x plus iy. So there are two ways to expand this. You can say Z is x plus iy. And get some information. Or you can say, well, Z in its polar format and get a bunch of other uh, results. So let's first say Z is this. What happens if we apply this Z squared on it? Let's see what happened. The modulus of Z became squared, and the argument, which was theta, became 2 theta. 2 theta, right? So that, by the way, gives us this beautiful information that if we apply Z squared to this ray, then the argument is theta, all right? When you're talking about the ray, this theta is fixed. You can have different points, of course, but this is fixed. If you apply Z squared, what happens to this ray? What is the image? The image will be this one in UV plane, 2 theta. Instead of theta, it will be 2 theta. So any ray, when you apply Z squared, will be another ray, but this time the angle will be twice. So that's a good information, all right? Now keep that information. Now, what if we let Z be x plus iy? Oh, let's check. If I will let Z be x plus iy and square it, we get this. This is the real part, and 2xy is the imaginary part. That is going to give us a bunch of other results. Here is U, here is V in UV plane. Well, another question is, for example, what happens to this vertical line in XY plane? In XY plane, this vertical line, if we apply Z squared, what do we get? Okay, what do we get? Well, here is what we get. The equation of this line is x equal a. So you replace x to be a. When you do that, you will get these equations here, which is parametric equation of the image, all right? I replaced x by a here and here. So u is this one, v is this one, and the parameter is y. Y can be anything, right? Here, look at the picture. Y can be anything. This is parametric equation of the image of this straight line under z squared? Well, look at this. From here, I can say v is 2ay, right? So we can have y. By eliminating the parameter, we get an equation in terms of u and v. So I will solve the second equation for y, plug it in here, I will get this equation. It's an equation in u and v. This is a curve in UV plane. This is actually a parabola in UV plane. And here is its image. So this line equal this vertical line, when you apply the function z squared, becomes this parabola. This a, of course, becomes a squared, right? And here we can also find these 2 points, which is when u is 0, you will get v squared over 2a is a, so this is 2a squared. This point is 2a squared. This point is negative 2a squared. Anyways, so this is what I meant by using the polar format of z. You get certain properties. Then using x plus iy, you get some other properties. So we will do both of them. So right now, I know that the way z squared works, it sends this ray theta to this ray 2 theta, and it sends this vertical line x equal a to this parabola. Okay? Now, what about a horizontal line? Oh, well, let's find out what happens to a horizontal line. Here's a horizontal line, y equal b. Remember that u and v? In u and v of z squared, we replace y equal b, we get this, which is a parametric, again, parametric equation in UV plane. The parameter here is x. If we eliminate x, this is what we get. You find x from here, plug it in here. You get an equation in u and v. This is again a parabola. This is a parabola, but the parabola this time is right here. So this horizontal line, y equal b, you apply z squared. Oh, this is b e to the I pi over 2, right? The argument pi over 2. Then apply z, this point becomes b squared e to the I pi, right? Let me write it down, make sure that we understand what's going on. So this point right here, the point b e to the pi over 2I. When you square it, it becomes b e to the I pi. And e to the I pi of b squared, of course, is b negative b1, so negative b squared. So this point, the image of this point under z squared is right here. Well, this time this is the parabola, okay? Opens toward u-axis. Good. So we know what happens to rays. We know what happens to vertical lines. We know what happens to horizontal lines, okay? Then I can now do this. The question is, what happens to this region, which is bounded by x equal 1 and this ray? If you apply z squared, this vertical line becomes this parabola. This ray, which is theta equal pi over 6, this angle here is pi over 6. This ray becomes pi over 3. So this region, this shaded region, if you apply z squared, becomes this shaded region in UV plane, okay? All right? Any comment, any question? This is the line theta equal pi over 6. That becomes theta equal pi over 3. Any comment? Oh, here's another one. This triangular region. Oh, you are going to have questions like this. I will give you this triangular or some triangular regions or any region. And I'll ask you, okay, find the image of this triangular region under z squared. What happens if you apply z squared? What happens to this triangular region? Well, this theta equal pi over 6 becomes pi over 3. This pi over 3 becomes 2 pi over 3, right? This is 2 pi over 3. And this x equal 1 becomes this parabola. So the image of this triangle under z squared is this shaded area, right? That is how interesting and at the same time challenging the mapping in complex analysis are. Okay. Any comment, any question? So here is another example. So the question is, they will describe a region for you. And this is one of the examples of your book. problems of your book. Modulus of z is less than 1/2. That means you have a circle of radius 1/2, and z has to be inside. Also, they will tell you that the argument of z, absolute value, is less than pi over 8, which means the argument of z is between negative pi over 8 and pi over 8. So we are dealing with this shaded area. Okay, we are dealing with that shaded area. So two conditions. They describe the region by these two conditions. And then they say, all right, map this by z squared. What happens if you apply z squared here? It's come, all right. Well, we know what happens. If we apply z squared to this one, it would be negative pi over 4. This will be pi over 4. And this circle, if you square it, 1/2 becomes 1/4. So the image is this shaded area, okay? The image is that shaded area. Any comment, any question? So this is the argument why the circle of radius 1/2, which is this. If you apply z squared, it becomes the circle of radius 1/4, because here's the circle of radius 1/2. You square it, you get this circle of radius 1/4. Okay. All right. Another mapping is conjugation. What is conjugation? So whenever you have a plus bi, its conjugate is a minus bi. So geometrically speaking, this is a plus bi. This is a minus bi. But r doesn't change, all right? Only theta becomes negative theta. The argument becomes, and that you can observe that one by putting it in this polar format. If this is z, the conjugate, r doesn't change. The whatever multiplied by I will be negative I. So theta changes to negative theta, all right? R stays the same. So conjugation geometrically is actually reflection with respect to x-axis, all right? So reflection with respect to x-axis. Conjugation is nothing but reflection with respect to x-axis. Okay. There is another motion. We call it inversion in the unit circle. What is inversion in unit circle? That is when uh, r e to the I theta will be sent to 1 over r e to the I theta. The modulus will be reciprocated, but theta not. And here is why uh, the unit circle comes into play. So all we do in inversion in the unit circle, we send r e to the I theta to z to 1 over r e to the I theta. If z is outside of this unit circle, that means r is bigger than 1. This is 1, right? Up here. R is bigger than 1. So 1 over r will become less than r. So this will be mapped to here as inversion in the unit circle. If the point is here, that means r is less than 1. As a result, its reciprocal will be bigger than 1, and this will be mapped here. Okay, that is inversion in the unit circle. So why do I need that? Because I want to consider the function 1 over z. The function 1 over z, when z is, of course, this. I plug it here. This is what we get. This is what we get. So there are two actions involved. One is inversion with respect to a unit circle, then you take conjugation, all right? So this is why I separated these two these two geometric motions. So 1 over z sends r e to the I theta to this one. Or you can look at it in this way. First, it sends r e to the I theta to this one, which is inversion. Then changes theta to negative theta, and that's conjugation. All right, so I'm trying to make things very simple for you. So the reciprocal function, the function 1 over z, is composition of two motions, right? Two motions. Now, this is good by, as I said, usually this is what we do. We use the polar format to get some ideas, some facts, some observations. And then we use z equal x plus iy to get more observations. So for 1 over z, here's 1 over z. When you replace z by x plus iy, this is what you get. Multiplied by the conjugate. So u is, the real part, is x over this. The imaginary part, v, is negative y over this. So u and v. Okay, what happens if x equals 1? What is the image of the vertical line x equals 1? When x is 1, this is what we get, all right? So v over u is negative y. Now replacing y by this, you get this equation. This is equation of a circle. Here is the circle in standard format. So x equal 1, this vertical line became this circle in UV plane. Now, I put both system together. So x equal 1 is this line. Got wrapped in here. Well, of course, it doesn't cover the 0. After all, 1 over z doesn't make sense when z is 0. But with this convention, we can take care of that, right? So infinity means, all right, the endpoints of this line get together and cover 0. So that is what 1 over z does to this vertical line, x equal 1. So here are more examples of 1 over z. For x equal 2, if you apply 1 over z, this point here is the unit circle. Or remember, 1 over z is composition of two motion, inversion and conjugation. So inversion of this is 1/2. Inversion of this point comes here. And then conjugation will give you this circle. So x equal 2 becomes this circle. Doing it geometrically, all right. I could do it analytically like that x equal 1, but this is good enough. More examples. What happens to y equal 2? Horizontal line. The horizontal line y equal 2 okay, we have inversion together with conjugation. Inversion of this line will be this circle. And this is unit circle, right? This circle is the circle of radius 1/4. Then conjugation bring it back. So here is what 1 over z does to y equal 2. This y equal 2 becomes this circle. Okay? More examples. Making the examples more involved. As I said, in your test and in your exercises, you will have a region of XY plane like this one. The question is, what happens to this if we apply 1 over z? Okay, well, you can think about inversion and then conjugation. Okay. Inversion of this x equal 1 is this circle. X equal 2, oh, sorry, x equal 2 is this one. X equal 1 is this. And then conjugation. Conjugation basically, remember, it means reflection with respect to y-axis. Okay? All right? Any question? Any comment? So right now, I sort of covered um, three functions, three as mapping. One was linear function. The other one was z squared, okay, z squared. And finally, I covered 1 over z. 1 over z is, of course, getting more complicated than, and as I said, we usually consider the uh, the polar format. If you use the polar format, this is what you get, which is combination of inversion and then conjugation. Inversion and then conjugation, all right? So, and if we replace z by x plus iy, this is what happens. This is the real part and imaginary part in terms of x and y. Of course, I applied this for x equal 1 and analytically showed you that x equal 1 under 1 over z becomes this circle in UV plane, which is a circle of radius 1/2, centered at 1/2 0. All right? Okay. Well, I will stop here. This section 1, 17.1 has a lot of material in it. So I touched these three functions, but next time I'm going to talk about 17.1 and some other beautiful facts in 17.1. You will enjoy those, all right. Here comes more examples. I guess we did this example. So yeah. So this is what I covered today. Linear function, z squared, and 1 over z. I covered these three functions. And next time I will cover z plus 1 over z, which is Joukowski's airfold, and that is an extremely beautiful function, as you will see on next Thursday. Any comment, any question? If you don't have any question, please go ahead and read that section 17.1 and start doing the problems. And as I said, I'm not completely done with that section, though. I will probably finish that section on next Tuesday. Number 3 of 16.4. Sure, let me check. Let me see. What do we have in number? Let me bring the text and see what do we have there. $16.4, did you say? Number 3. Yeah. Oh, this integral 1 plus sine theta divided by 3 plus cosine theta. Good. Sure. This is a very good one. It's a very good one. Let me, at least I will set it up for you, Gail. And I'm just give you the hint as how it's done. So it's integral 0 to 2 pi 1 plus sine theta divided by 3 plus cosine theta. Oh, remember, we are going to convert this to the integral over unit circle. And by this change of variable, e to the I theta, when theta goes from 0 to 2 pi, z will cover the whole unit circle. But in the process, this becomes, all right, the integration over unit circle. One plus sine theta will be z plus minus, actually, to the negative 1, 2i. This is sine. Cosine will be 3 plus z plus z to, and this theta will be the z over I z, right? Okay, good. Now, of course, you need to simplify this. Especially we need to sort of get rid of these twos, right? So if I multiply by 2i, numerator and denominator, 2i and 2i. The next step, this becomes integration over unit circle. This will be 2i in numerator, z minus 1 divided by, this becomes 6i, right? Well, I will multiply just by 2 and keep the I, and this I will give me negative 1. So it will be 6 z. Oh, that's negative up there. Yeah. And here, So I dz over z. Next thing you want to do is get rid of this z to the negative ones. So you multiply by z and divide by z. So this is what I'm going to do to get rid of this. So it will be negative integration over unit circle or remember we have another z here. So I'm going to now consider that z. Multiplying this by z, you get z squared plus 6z plus 1. And multiplying this by z, you get z squared plus 2i z minus 1. Good. Now we are there, right? So this integral, by this change of variable, was converted to this integral, which is an integral of a complex function over z equal 1. Now, here we are talking about integration over this unit circle, right? And we know what happens. The integral will be 2 pi I, sum of the residues of the singularities that are in here. One singularity is z equals 0. The other one will be the roots of this guy. So let's find out. When z squared plus 6z is 0, you will get the roots nine minus 1, which is 8. So we have two roots, and both of them are real, but -3 negative square root of 8 is way outside. The one which is inside is -3 plus square root of 8. So -3 is outside. So the integral will be, I'm just starting with this, negative on unit circle whatever this we have here, all right, I'm not going to repeat this one. 2 pi I, so negative 2 pi I. Let's call this one f of 0, right? So I can some of the residues that are the poles that are inside. So residue at 0 plus residue at -3 plus the square root of 8. Now, both this 0 and this one are simple poles, right? Both of them are simple poles. So, as a result, the answer, which we started from 0 to 2 pi of 1 plus sine theta divided by 3 plus cosine theta d theta is -2 pi I. Oh, residue as 0. And well, since it is sum of these two residues, that's just okay. Since those are simple poles, then we can use the, you multiply by z, okay, the residue at 0, I can easily find that. You multiply by z and then plug z0, you get -1. And residue at this, okay, residue at that one, it's just a matter of computation, all right? I think you can do it, Dell, can't you? You can find the residue, can't you? So we found the answer. Right, exactly. You can use 2b. That's good. That's good. And 2b, remember, it's going to be numerator divided by derivative of denominator. And after finding it, you simply replace z by this. Okay, sure. So that's it. That will be the value of this problem number 3. Oh, my pleasure. Yeah, I'm glad that we had time today. We could do that. These are the process. The process is pretty obvious. I have explained it, but sometimes it might be a little bit manipulative. You need to do some algebraic work to find the, for instance, like this one, the residue at that point. Okay. Okay. Any other comment? Any other question? If there is no question, then I will see you on next Thursday. Bye-bye, everybody. Thank you, Matthew. Thank you, Brandon. Thank you, Krish, Corey. Thank you. Thank you, Dell. Or Tuesday, why not? Is there something special going on Tuesday? Oh, my mistake. At the end of the session, I'm a little bit tired. No, see you next Tuesday. See you next Tuesday. You too. You too. Bye-bye.